Hi, this is Peter with CalcBook, and today we're going to be looking at simple shear connections, and specifically we're going to be looking at an all-bolted double angle connection or a double angle shear tab. So really what that looks like is we're going to be looking or kind of referencing the AISC manual part 10, and we're going to be trying to basically kind of replicate the values found in table 10-1 as sort of our baseline, and then we'll look at a couple different variations of that. But we'll start with that so that we can confirm that our calculation is correct, and then we can start adding in more complexities after that. I will also be using the AISC specification, chapter J, right, for our bearing, bolt hole bearing and tear out and that sort of thing. So let's talk a little bit about the different design checks we are going to be looking at for a double angle shear tab or all bolted double angle shear tab. So we're going to be looking at bolt shear, direct shear, and if you're using a slip critical connection, then it'll look at the slip resistance, and that is an option in CalcBook if you are using slip critical connections. We're going to be looking at the bolt hole bearing and tear out, and we'll be talking about sort of the references and how what equations and calculations we use there, because there's a little bit of nuance in how to calculate that capacity. And we're looking at the shear yielding of the angles and the shear rupture of the angles, and then also the block shear rupture of the angles. And then there's two additional things that we check in CalcBook that are not part of the tables, and that's going to be bolt hole bearing of the beam web and bolt hole bearing of the column web. There are quite a few additional checks that you would need to do in the beam, but considering all the different configurations, if it's single coped or double coped or however you have your beam set up for that connection, the calculations can vary quite a bit. So we'll leave that up to the user, but we check everything related to the double angles and the bolts for this type of connection. And so in order to use table 10-1, right, we sort of need to have this conventional configuration for what is considered a simple shear connection. So the first of those is that our A distance has to be less than or equal to 3 inches, single vertical row of bolts, and then we are using standard or horizontal slotted holes. And then additionally, to compare directly with table 10-1, we will assume the following just to compare our answer, which is going to be the vertical spacing to the edge is going to be 1.25 inches, the horizontal spacing to the edge is 1.25 inches, and the spacing between bolts is going to be 3 inches. So let's take a look at our problem statement for today. We have a W18 by 143 beam that has a web thickness of 3/4 inch, 0.75. We're using 3/8 thick angles. We are going to be using 3/4 inch A325N. So the shear planes are not excluded. The thread planes are not excluded from the calculation, and that's going to be in a standard hole. Our A is 3 inches, our L sub EH is 1.25, and our L sub EV is 1.25, like we just said, and then our bolt spacing is 3 inches. And we have a very specific shear load there of 105 kips, because that's what we're going to be basically trying to match in the tables. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we've got CalcBook open now, so we can go ahead and jump into our 15th or 16th edition steel module. We'll use 15th edition for this calculation. Click into our connection design, and then we'll click on our double angle shear tab, click confirm, and get that loaded up. So we can start going through our inputs here on the left side. Right, as I said before, you have the option for a slip critical connection or a bearing type connection. If you do click on slip critical, there's going to be a few other things you need to select. Your type of filler material between the connected parts, your surface prep, and then there's some torque requirements and some other things down here as well. So just be mindful of that if you do select the slip critical connection. We are going to assume that deformation at bolt holes is a consideration during design. We're going to select our 3/4 inch bolts, and it gives us a warning because our hole size is too small, so we'll go down to 1/16 over for our standard hole. We have 3 rows of bolts. We are going to be using our A325 when threads are not excluded, so we'll be using that 54 for our shear strength. Leave our block shear coefficient at 1. And then our A value is 3, our spacing is 3. We need to adjust our LEH and our LEV to 1.25 inches each. Our beam thickness is going to be 0.75, and we can just assume it's 65 KSI FU. And then we're going to leave our shear tabs at 3/8 thick, and we'll use 3658. And then we'll go ahead. We didn't say it in the calculation or in the problem statement, but we'll just assume that our member 3, our supporting member, our column, has the same thickness as our beam, just for purpose of calculation. And then what we're going to go ahead and do is enter in our demand of 105 kips. And we can see right already we're at 104.6 of capacity. Our demand is 105, and we'll look at the table here. I'll overlay it in a second, but the tabulated value for this is 105 kips, so that matches. So now we can go ahead and step through our calculation. Right, the first thing we're going to look at is our shear strength of the bolts. Pretty straightforward. Right, just getting our shear capacity for the entire bolt group. And remember, this isn't double shear, so we multiply our values by 2 because we have 2 angles, one on each side. Then we look at our bearing capacity, right? So we do check all 3 components. So we check the beam web bearing hole capacity. We check the double angle bearing hole capacity, again multiplied by 2 because it's a double angle. And then we also check the bearing hole capacity at the supporting member, the column in this case. Now let's talk about tear-out capacity, right? We have the tear-out capacity of the bolt hole. But when we actually look at the total tear-out capacity, it's not just the tear-out capacity of the bolt holes or in between the bolt holes. For common configurations where the bolt spacing is 3 inches, typically the tear-out between bolt holes does not control. So there's a very good article in AISC Modern Steel Construction, the May 2017 issue, that discusses this topic. And basically what you end up doing is you check a couple different things, but the sort of final calculation that you do to determine the total tear out is going to be the tear out of nearest the loaded edge, so this tear out capacity, and then you're going to take the minimum of either the bearing hole failure or the bolt shear failure of the other 2. So you figure out what that is there. So we look out here, right? We have our tear out capacity of the bolt nearest the edge, and then we take the minimum of our bolts in double shear, our bearing capacity of the beam, and then our double bearing capacity of the angles. So whichever controls of those 2, you'll add those 2 up plus the tear out of the loaded edge, and that is going to be your total tear out capacity. So again, I'll post a link to the Modern Steel Construction article. It's a really good breakdown about how this is calculated. There's some other checks in there as well, but this is how you kind of finish out the tear out calculation. And then we go to the shear yielding of the member. Pretty straightforward calculation. We've done this before, as well as the shear rupture as well. We've done that before. And then finally, the block shear strength of the double angle, which we saw before. So last few calcs there are pretty straightforward, but we end up with a capacity of 104.6 kips. And if you look at the value, the tabulated value in the table 10-1, you'll see that they have 105 kips there for the capacity of this configuration. So we also list those failure modes in the calculation notes here, talking about what we check and what we don't check in this calculation. So be sure to check that out as well. So that is a double angle shear tab connection in CalcBook. I hope you guys enjoyed the video. As always, if you are still watching, we would like to offer you a 25% discount on your first month subscription. You can use the discount code YTCB2024, and you can use that during your checkout. So thanks again for watching, and we'll see you next time.